Hi everyone, welcome back to week 8 of Techquitable Futures. This week, we're going over the topics of sorting and searching. So let's start with the introduction. Max, do you want to give an intro of yourself?
Yeah, sure. Is my audio all right for you guys? Is it smooth enough? Okay, cool. Yeah, so my name is Max. I'm currently a software engineer at Google. Went out, did you want me to kind of do like full story from graduation or?
Yeah, that would be great,
Okay, sure.
actually.
Yeah, so I grew up outside of Dallas, Texas, and I went to school at Texas Tech in West Texas, got a degree in computer engineering there. And then I went to work at a company called National Instruments in Austin, Texas. And while I was there, I was doing mostly like driver development. So that company is kind of a test and measurement company, and they do like software, hardware platforms for doing test and measurement. So these platforms, you might find them like at the end of an assembly line, doing like really high-speed measurements of integrated circuits, small computer chips, where you need like huge number of things flowing through, and you want to test like all of their ins and outs as quickly as possible and get through. And you might also find them in like a scientific experiment where you need like high precision, high frequency measurements. So I know that their equipment was actually used in like whenever we detected gravitational waves. That experiment was actually like some piece of it was in with National Instruments equipment. So that was pretty cool. I worked as a driver developer on the PXI platform, which is a lot of like interfacing between the actual hardware and the operating system. Learned a lot about operating systems and stuff. Did a lot of C++ there. And but I kind of had this feeling that I wanted to go a little bit higher level and kind of wanted to do a little more web. I think most of all, I wanted to do something that actually, I guess, a little bit more directly impacted a user. So when I was doing the driver development, it was very much like if your thing didn't crash, then that's when I was doing my job correctly. But no one was going to be like, wow, those drivers sure are awesome on the PXI platform. So that was like one thing that led me to wanting to do something a little bit more web focused. And yeah, I started interviewing around, and I did actually get a position at Google. And so in the Portland, Oregon office. So that's where I am now, moved to the West Coast. So after 3 years at National Instruments, I have been at Google for almost 4 years now. Type of projects that I'm working on now, since joining, I've worked on the front-end server for the Google Home app. I'm in the Google Nest org, so I'm still kind of in the hardware software mix, which I enjoy because I like having the physical product to look at. But I'm doing a lot more of the server-side development. So yeah, there's a server that the Home app hits first before going out into the various like microservices architectures and all the other services. And that's the server that I worked on when I first joined. And then I started working on a newer subscription service from Google called Nest Aware. So it's what you would subscribe to if you wanted to like have continuous video recordings instead of just event-based video recordings on your Nest Cam. Specifically, the feature I got to work on was E911, which enabled emergency calling. So if you like your smart speaker hears glass breaking, and you look at your Nest Cam in response to a notification, you see there's an intruder, but you're like 2 states away. You can click the call emergency services, and it links you through a proxy number to the dispatch center closest to your home instead of closest to where you are. That was very cool for me, like just knowing that even if it's not used that often, if it does get used, so like someone really making, they're making an emergency call because something's wrong. So I find that super interesting and encouraging. And now I'm doing kind of growth stuff. So instead of on as much server development, it's more like pipeline development. So collecting like user analytics and developing tools for promoters to run promotions for Google Home products and whatnot. I don't know if any of you might be aware, there's a thing that happened last like December, I think, where if you had a Spotify subscription, then you got a free Google Home Mini. We gave out a ton of devices that way. That was actually my team that did that. So yeah, stuff in that vein, coupon infrastructures, things like that. And I think that's it.
Sounds good. Yeah, thank you for your intro. Yeah, I really appreciate kind of like yeah, having you share your background, and I think it's really interesting and relevant to a lot of students here, since the students in a cohort have learned like low-level languages such as like C, C++, and Java in classes, but a lot of them also trying to like figure out, okay, what do I go, or what do I need to do to go from where I am to go into more like web development. That's what's like, with a lot of these job opportunities available at these bigger tech companies. So they give you like, okay, your kind of journey to go from, doing low level programming with hardware to more of like the software side, working on like cloud or like, web applications is really interesting for some students. So yeah, so if you have any questions about Max's background or how he did it, feel free to kind of like ask him in the Q&A toward the end of this lesson. Yep, but thank you for your intro, Max. And we originally had one more instructor named Noah Morrison. Unfortunately, his travel plan just happened to collide with our lesson today, so he won't be here to present. But in his place, we'll be presenting his parts of the lesson. And this is a cool fact, in case you haven't noticed, but Noah Morrison's brother, Adam Morrison, was one of the instructors that gave the lesson on the topic of arrays and strings back in lesson 4. So Noah is Adam's brother, and his travel plan is actually to go drive cross country to meet up with him. So yeah, that's a little interesting story about them. All right, anyways, so that's it for intros, and yep, let's get going then.
Cool. Yeah, so we're going to be talking about various types of sorts, various types of searching, and then going through some interview examples. So we'll start with the bubble sort. This is one of the more simple ones. So the basic idea with the bubble sort is that you have your unsorted array, and you're going to go from left to right through the array, and you're only going to look at 2 elements at a time. So you can kind of see this animation here going on. Whenever you see that the greater number comes before the lesser number, that means they're in the wrong order, so you do a swap. So you just keep on doing that over and over. You see there the 6 actually stopped because the 8 was greater. Now we're going to start swapping the 8. And so you kind of get this bubbling effect where the biggest number will bubble to the top after one iteration of that array. So here the biggest iteration, the biggest number in the array is 8. So during our first iteration, that 8 is going to end up at the end. And at the same time, you had some of the other bigger numbers bubbling up. So I think the visualization is kind of like, if you ever had like a fizzy drink and you see the side where there's bubbles and they're kind of like racing up to the top, they all get there eventually. That's kind of the visualization going on here. After one iteration, we know that the biggest number is at the end. So we start at the beginning again, do the exact same thing, but we'll stop one short of the end. And now we know that the second biggest number will be at the second biggest position. So then we just keep on doing that. Each iteration takes one less step than the previous iteration because we already know that the biggest element has made it to the top from the prior iterations. And if we keep on doing this over and over, we know that there'll be no more swaps to make, and we have a sorted array. Yeah, so for runtime, can we get a guess of, in one iteration, one pass through the array, how many operations are occurring? Chat or voice, welcome.
Yep, we've got one chat submission in the chat room, but if anyone wants to voice it out, feel free.
Yeah, we've got an O squared in there. Yeah, so that's going to be the eventual overall runtime of this, yeah. So in each pass of the array, yeah, first case, or maybe one question is, what's the worst case that we could run into? What's the worst scenario that this algorithm could run into? What about the array would make it the worst?
In reverse order?
That's right. So if you're in the reverse order, then every single operation is a swap all the way to the end. And you have to start over. Every single operation is going to be a swap again, because you have to like move each element from the position all the way to the end every single time. So yeah, each run through, it's going to take in swaps, and then you have to do it in times, which is what you get that nested for loop, and you get that O n squared runtime. In operations, in pass, O n squared. So that's bubble sort. What about in space? I'm not sure we looked at space. What would the space complexity of that algorithm be? Got an O of 1. Yep, and it would be O of 1 because you're just swapping. So whenever you're doing something entirely with swaps, you don't have to do any extra arrays, any extra storage, so constant space. So moving on, we have selection sort. So in this one, we're basically building up the sorted array from the left. And so we're going to do swaps. And each time we do a swap, we want to look through the array, the unsorted portion of the array, find the lowest element, and then swap it into the first position in our sorted partition of the array. Here you can kind of see that happening individually. I feel like this might be how I would sort if I were given like a deck of cards or something. Just find the lowest number, put that at the front, find the next lowest number, put that next to the one. So it's kind of a scan and swap, as opposed to swapping like at every single step like the bubble sort. And at the end, you will have your last element there, and it's all sorted. Yeah, so you can think of it like you're sorting the whole array, and so you're going to like take the smallest number, put it at the end of your sorted partition, and now your sorted partition has grown by 1 while your unsorted partition has lessened by 1. And you're just continuously moving from the unsorted to the sorted. Any guesses of the time complexity of this one? Yeah. It's very similar to the sort look swap. And then we start over at the beginning, look through the whole entire array again, do the swap. So that scan, since we have to do that scan every single time for each element to find the one lowest element, then we get that O n squared behavior. The nested for loop action. So it does get shorter and shorter as you go on the scanning portion, because your unsorted array is shrinking, but the overall worst case, you still get that O n squared. And this one would also be, as far as space complexity goes, this is only using swaps, so this would be O1 in space as well, because it's an in-place sort. I'll go into merge sort. This is where we start to get more efficient than O n squared. So merge sort is very much one of these divide and conquer algorithms. And so I think the observation here is that if you have two sorted arrays, you can merge them together in linear time. So if we can break our problem down until we're only dealing with sorted arrays, then we can just repeatedly merge the sorted arrays until we get our final sorted array. And so here you can kind of see in this visual, we're breaking down that array until it's just singles. And now at each of the merge steps, you can just look at the head element of each of the sorted input arrays and just pick the lower one over and over. And because they're in sorted order, you know that the next lowest element is either going to be at the head of one of the inputs or the other inputs. So there's no scanning that has to happen there. You just take one off, take one off, take one off. And then once you have your two input arrays sorted, then you have another array that's twice the size. Then you can move on to the next step. And now you have two slightly bigger arrays that you can merge. You just keep on repeating that over and over. Kind of a tree helps visualize things. You can see there's this divide step where we're just repeatedly breaking it in half until we have arrays that are one element, which is by definition a sorted array. And then we can begin our conquer step of divide and conquer and just merge each one by picking the lowest one at a time. So what do we think the runtime would be of dividing the array? Until no more can be divided.
Log in.
Yeah, there would actually be a login function calls that have to be made. And that comes from that tree structure. Oops. Yeah, and then actually the breaking, all you have to do is kind of find that middle index. So that's a constant operation. And then you just call yourself again recursively to the left and right. So it comes down to more the function call being the expensive part. And now merging the smaller lists into a new list. So if we just look at one step, say, let's look at these, the 2738, 343, merging that into a size 4. What's the runtime of just that merge operation? And yeah, exactly. That's because that comparison of which has the shorter element, 3 or 27, it's 3. That's one constant comparison. We're only looking at 2 elements at a time. So that can be done in constant time. And then we just kind of move ahead the 3 pointer to the 43. Now we can do a constant operation again. And so at the end of that merge, we've looked at each element just once and then copied it into our output array just once. So that's like a constant comparisons, constant placement, but then we do it for just once for all of the input elements. So we get linear. And then for the merge step, very similar to the divide step, will be log of n as well, right? So it's, we know that a merge happens in linear time. So then it's how many times do we have to do that merge? And the number of times we have to do that merge depends on how many layers there are in this tree that we've broken down by 2 every single time. So if we have to do a merge, which is linear time, log of n times, then we get this n times log n, runtime for a total of n log n. Does that make sense to everybody? Great. Now, what about the space complexity in this one? Anybody have a guess?
Would it be O of n?
Yes. And that kind of comes from the fact that when you are doing the merge, you have to have this output array to merge into. So you're actually doing a copy into that second array. And the length of the copy that you're generating adds up to the size of the input as a whole. So you end up with like a sorted array that's actually a copy of the initial one. You didn't get to do it in place because you're doing more than just swapping. So that one, may seem obvious that the in-login runtime is better than your in-squared runtime. However, you are actually using space, so something to consider. I have a question. When is it at the worst case? Yeah, I think the worst case here, as with most sorting algorithms, is going to be when it comes in reverse order. However, I think with the merge sort, you actually end up doing the same operations no matter the ordering. And that's because even if it was completely sorted, the algorithm still splits everything apart and it still merges everything. And the part that you're saving with it being, coming in sorted or coming in out sorted, reverse sorted, would just be like in this comparison and picking this lowest element from each array. But that we talked about earlier, that part of the merge is not actually the expensive part. Like picking the one that's lower in the merge is not the expensive part. You still are just like looking at each element in those input arrays, which you would do whether it was in reverse order or sorted order. So you actually get the same kind of across the board, best case, worst case behavior here.
Yep. Just to follow up on Max's point, merge sort is also known as a stable sort, which means that it has the same runtime for both average case and the worst case. However, there are like other sorting algorithms in which the average case and the worst case isn't the same, where worst case could be could have like a higher runtime if it's like fed in like a certain types of input where, for example, like array is reversed in a completely different order. So, some examples of that is like a bucket sort, which is not covered in this lesson, but it would have like a average time of like O of n plus k being like the bucket number of buckets, but then the worst time would be like much higher than that. So something to point out, it's goes into like a deeper details of the sorting algorithms, but it's good. You just I think one good thing to keep in mind is merge sort is a stable sort, and it's going to have a runtime of all of n log n.
Yep. And then I think one of the most important things to remember when it comes to sorting is that we don't really have a way to go faster than n log n. So whenever you think in an interview or something, this problem would be a lot easier if I had something sorted, then you can usually just say, let's say we just sort the array, and you can count that as an n log n operation. And most of the time, if you have an interview like where you would like to sort your input before proceeding, you just have like a dot sort or something. So the actual implementation is a lot of times not as important as knowing that sort is n log n in most cases.
Yep. And to follow up on that point, Max is right. For standard cases, you can assume that the sort is going to be of n log n. However, there's like one exception in which you can run sort in an O of n time, what's known as like radix sort or a bucket sort. But certain conditions have to be met, such as like having like a predetermined like number of buckets or keys up front. We're not going to go into the details here, but I'll just post a link in case anyone's interested in like learning about it. But just to kind of re-emphasize the point, for the most standard cases, especially in an interview setting, you can assume that merge or so any kind of sorting would take over n log n.
Yeah, and I think just one last thing that is pretty interesting about merge sort is that this divide step, when you talk about really big input sizes, because you're doing a divide and conquer, we'll say, so you back up. A lot of times when you're in an interview and you progress to the like very end of the question. One of the questions might be like, okay, now what if the input, what if you have so much data that it won't fit in memory? Merge sort is something that can like actually be used even in that case because of this divide and conquer. And actually, it actually can be parallelized as well across multiple machines because you're doing this like divide and conquer. So you can imagine that if one computer was doing all this work, it's going to be in log n and it has to do all the sorting. But if we were to like partition our array and actually send that to other computers, we can get things done much more quickly. So that's an interesting thing about this sort. There's implications beyond what you can do with like a single computer with these algorithms. Linear search. So we're moving on into searching. So typically with your searching, let's see. Sorry, the Zoom windows all over the place. Okay, so this is usually when you have some input data. It may or may not be sorted to begin with, but then you are tasked with finding some element, maybe the index some element within that input array. So with your linear search, this is kind of like your most basic naive way to go about it. I say, find me the number 20 in this input array. So you just start at the beginning, look at each one until you find the 20. Once you found it, then you return that index. So a question for the audience, what would the worst case be for this sort of searching algorithm? Any ideas? Yeah, let's do runtime. And that O of n, that comes from the worst case, which would be like the item you're looking for is at the very end. So you actually have to touch every single element in the array before you find it. Good. The worst case, obviously the consideration of is this the element is just a double equals, single comparison, that's constant. So we get O of n. So one faster way that we might be able to search is with a binary search. I don't know if this is actually linking to this video or not. I don't think if I click on it, nothing happens.
Oh yeah, there's a link at the bottom where it's highlighted in blue. It's video.
Okay.
Yeah. For the students, yeah, this is a video that we actually watched in one of the earlier lessons where Professor of Computer Science at Harvard, David Malin, he started ripping up like all these like phone books pages in order to find a guy named Mike Smith. And the kind of whole point of like ripping up the phone book in half each time to find that one record was to just show you how you can cut down the search space into half each time to kind of like expedite your search process. So if you want to watch that fun video, there's a link that takes you right to the part where it's like ripping the phone books. It's fun to watch. It's fun to watch. But yeah, I mean, this time we're actually coming back to this concept of like binary search. So let's hear what Max has to say about this.
Yeah. I think the first, that phone book analogy is a really good one. If you're looking for something in a dictionary or phone book, you know that it's sorted by something like last name or something, and you are looking for somebody whose last name starts with R or something. You might just flip to the middle of the book, see like, okay, I'm in the I's. So that's like what I'm looking for is going to be later in the book. So you just totally shrunk your search space by half because you know I no longer have to consider anything in the front half. You just keep doing that over and over until you narrow in. So let's see, this might be a bit of a technical slide. Yeah, the idea behind the algorithm is that you have your kind of low and high, and at the beginning, your low and high start at the start and the end of the array, and then you calculate the midpoint, which would obviously just be like the average between the two. So add them together, divide by 2, that gives you the midpoint of that partition that you're currently considering. And then you look and see what's at this position. If it's what I'm already looking for, then I can stop early. Otherwise, I need to check to see if it's lower or higher than what I'm looking for. And if what I'm looking for is lower, then I know I need to look to the left. If what I'm looking for is higher, I know I need to look to the right. And so that is when you reset your low and high pointers. So if you want to look to the left, you basically slide your high pointer down to the midpoint. And now you have a new low of high that just looks at the left section of the array. And then the opposite if you need to look to the right. You're just going to keep doing that, and eventually your range will be locked into where exactly what you were looking for, or you haven't found it. And so you can do that. Your algorithm will basically end by checking the difference between your low and high. If high went like lower than low, then you know you've gone too far and the element doesn't exist. Eventually, midpoint will fall on basically on your low and high. Yeah, so each time you run, things shrink in half. And this gives us a log of n behavior. And that is because we get to shrink our search space in half every single time. So just like the merge sort, when we have that like tree-like behavior, the levels in the tree are what determine the runtime, and that's going to be a log of n.
When are we at the worst time? I mean, yeah,
Sorry?
worst case. When are we at the worst case for binary search?
Yeah, the worst case for binary search, if you think about like what forces you to keep moving on, is that you don't find it at the midpoint. And so it would be where you have to like shrink your input size by half over and over and over until you are like at a input size of only 1, and that's what your element is. So I think it would be like, sorry?
So maybe when we're trying to find 91?
Sorry, can you repeat that?
I said maybe when we're trying to find 91. Like if you look at the array.
Oh, 91.
Yeah.
Yep. Yeah, I believe that's given this example here, yeah. 91. It's basically like just off of one of the midpoints or of the input array.
Yeah. Okay. Thank you.
Yep.
Okay.
And then to add like another case to it, you could also imagine a case in which like your input doesn't contain the element that you're looking for. In which case your binary search will keep looking until the very last element, and then realizes that even the last element isn't the element that you're looking for. In which case, by that point, you would have like kind of like searched like all the possible candidates and still haven't found it. So that could also be your worst case scenario.
Yeah, there's a few worst case. I think it would be maybe kind of interesting to color the midpoints by like how deep they are, how deep they would be in the binary search to consider. You get like the very midpoint of the array would be considered immediately, and then the midpoints to the side would be considered second, and then the 4 midpoints there would be considered third. So there's actually like multiple worst cases, and they're usually like one to the side of the like subsequent midpoints. There's actually multiple worst cases. It's kind of interesting. I think this is kind of going over the implementation. Yep, so we start with our low and high, calculate our medium, choose to go left or right. Yep, and keep going until low and high pass each other. Here's that iterative solution. Maybe take a minute to look at this. Any questions come up around this implementation? Here's the same thing, but recursive. So in the prior example with the iterative, we were storing low and high in some variables, but we could also just kind of call binary search itself again. So if we know that we can do a binary search on the left half, so that means we can just like call ourselves again with those low and highs reset. Cool. Little runtime summary. So we had our own squared for bubble and selection, but the merge got us log in. And then the linear search is going to be linear time in the name. The binary search gives us log in. One interesting thing to note here is that linear search is linear time, but it didn't require the input array to be sorted beforehand. Whereas the binary search, it requires it to be sorted, because if it's not sorted, then we can't make that decision of like, oh, I know what I'm looking for on the left or on the right, because it could be anywhere. So that's one thing to note. Like if you're in an interview and something is coming in unsorted, but you know if it was sorted, you can use a binary search. Your algorithm will require you to sort it first and then do your search. So the sort is going to be the more expensive operation at in log in, and so that's going to dictate your complexity. So just something to note there.
I have a question.
Sure.
So we know that merge is a better sort and log in at the worst case. Why would we even consider using bubble or selection if we know those are going to be slower?
You're asking when we would consider them?
Yeah, so we know that merge sort on the average and worst cases and log n. I'm saying, why would we consider bubble or selection if we know that those are slower?
Yeah, I think that the only consideration that would like make you choose one of those is if you have to do something in place without using extra space. That said, I think there are probably some in place divide and conquer methods. Like I believe quicksort is in login as well, and it is in place as well. So that's why like these sorting algorithms are almost just kind of academic, educational. It shows you like here's some bad ways that might seem intuitive but are not the fastest way of doing it, but you never actually run into them in practice. One consideration you might take into account is that just like in a practical sense, if you're doing a software engineering job, sometimes you need to do like a quick sort, but you don't really care. Like maybe there's something else way more expensive happening in your overall process, to where even if this sort is not the most efficient it could be, it's really fast to implement because it's just a nested for loop. Something that comes up a lot, I think, with that is like a linear search. It's like, okay, I have 10 elements. Maybe it's not the fastest for me to do a linear search, but I'm dealing with like millions of requests and stuff. Like there's a lot of overhead that's way more expensive. So even if I made that more efficient, my whole thing wouldn't be more efficient. So that's kind of like a practical consideration. But I also think in practice, a lot of times you are just calling a helper method that's like dot sort, and it's going to be using actually like a combination of different algorithms depending on the input size that all come down to n login. So
yeah, and then we actually got a great question here. So Wilmer asked, if an input is almost sorted, would we want to use bubble or selection, since merge is always going to be n log n for both best and worst case scenarios? Max, do you have any thoughts on on yeah, which should be preferred for the special scenario where the array is already almost sorted, but perhaps one, except for like one or few elements.
Yeah, almost sorted. Yeah, I'm not sure about that one. It's a good question. I'm not sure that how often that comes up. Like you're given something that is known to be almost sorted. I would think bubble, just because like bubble nudges things into place iteratively. And so maybe if you are able to like nudge it and then you do a pass without having to do any more swaps, then that might give you a better like overall runtime. That could be interesting to do some like profiling on and experimentation.
Yep. And actually, yeah, and one algorithm that isn't covered here today, but would really be effective in the case that Wilmer mentioned is an algorithm called insertion sort. Apparently for that, when you run against an almost sorted array, you can get the best case runtime of O of n. But this is like what we meant also, like what we mean by there are some stable and unstable sorting algorithms, because like with like things like insertion sort, you could get like a best runtime of O of n for like an almost sorted array, but in the worst case, you could still end up getting like O of n squared. And same thing with regards to like what Max said about quicksort. Quicksort is very similar to merge sort in that it also kind of like adopts this like style of like divide and conquer, but it does it in place. So in terms of space, it's even more effective than merge. And on the average case, it also runs at O of n log n. But unfortunately, quicksort has the worst case runtime of like O of n squared, which makes it kind of like worse than merge case in that worst case scenario. So it's interesting because like I mean there are like all these like sorting algorithms like and honestly you can like probably like do like an academic research on this and try to even like push the boundaries of it. But yeah, there are like all these kind of trade-offs that that you might want to know about if you're like working with like big data structures for your work and you're thinking about sorting all the time. But yeah, I think this is just like something that would be good to keep in mind.
Yeah, and I think the note about like if it's almost sorted, yeah, it's kind of like writing something to detect that something is almost sorted may actually cost as much as the sorting algorithm to begin with. So you have to really know that it's coming in almost sorted, in which case like maybe you've added one element to a sorted array and you just want to like make sure you get it into place. You might use something more like a binary tree in that case, the binary tree insertion. Best at its worst when there's a problem. Yeah, I think that's true. It always kind of comes down to knowing your input and knowing what's best for that input. And most of the time, you have to assume you could accept anything with a sort of equal distribution. And in that case, yeah, you want to look for your best average time, which is typically going to be something like a merge sort. I won't click into these here, but these are videos that you may have seen. It's kind of like an audio video representation of the different sorts. And it starts with like different bars, and the idea is to get them all like sorted up in order. And you can kind of see how they get swapped around and visualize what's actually going on within the algorithm. So definitely encourage you to take a look at those, but also turn down your volume because the noise is pretty loud. Cool. I'll switch back over to Wintao. I'll stop presenting.
Sounds good. Let me just get set up here. Let's see, present, share my screen. Alrighty, can people see this? Yes.
Yeah, I can see
Okay.
that.
Okay, cool. All right, so kind of happy to go over the interview examples for today. So we have 3 ready for you. And first one is two sums. So I'm sure some of you guys are familiar. I know Horatio and Maria, you guys have submitted like your solution in the coding questions channel. But this is like a little bit different. So it's a variant of this question. So you guys might still want to like hear how it's different and how some of the stuff that we learned today could be used in it. So for those people that don't know what this problem is about, the problem goes like this. It basically says, given an array of integers nums and an integer target, determine if there's a pair of numbers in the array that sums up the target. So some examples here. So like, let's say if we have this input with nums equal to 2, 7, 11, 15, and we want to see if the array has this target number that can be summed to 9, then we return true for the first one because, as you can see, 2 and 7 can be added up to this target number of 9. However, with the other example below, where we have 2, 3, 11, 15, and a target of 9, this one is going to be false because even if you add any of the numbers together, they are going to be, not going to be summed to 9. So I'm kind of curious, and maybe I'll just kind of like point to both either Maria or Horatio, since you guys have already gone through this problem. But can one of you guys like name what the brute force solution of this would be? Yep, double for loop. That's the way to go. You can imagine. Yep, double for loop, nested for loop. You can imagine like trying to basically compute sum of like every possible pair and try to see if that pair is going to sum up to this target number of 9, right? Let's see, Maria, I'm going to pick on you since I know you have done it, but for like an optimal solution, what did you do to kind of cut down the runtime from, using double nested, or, using nested loop, which would be O of n squared, but you had a trick that could reduce the runtime, right? Let's see, would you like to share? Okay, well, let's see. Oh, I could just show it to everyone here. I guess the trick that that you could use here is to use a lookup table or hash map, and basically what you can do is store like encounter values, and for each value, then what you do is you look up its complement, which is like target minus the current value has already been encountered in its like lookup table, and if so, just return it, right? So this is kind of the optimal way because by, you're basically doing this exchange of like time and space complexity. So by introducing more space, you're cutting down this runtime of O n squared to just like O of n. Since you're just doing a single pass through the array. So that was kind of what the original version 2 sum problem is about, but this time it's a little different because now, like, let's say the requirement is that you cannot add any additional space. Then what do you do? Right, that's going to be the question. And because, as I mentioned, the optimal solutions uses a lookup table or additional space. So how can you do it without additional space, but it's not going to run in O of n squared? Anybody has any thoughts? Yep. So Horatio, you said maybe some kind of binary search because it's sorted. I think that's a good direction to go. I mean, especially since we are going over the topic of binary search today. Let's see. Can anyone try to like recite how that might work using binary search? Take a guess about how you could use like binary search here and just cut down the runtime. Any guesses?
But is our input always sorted, or array, is it always sorted?
Yeah, that's a good question to ask. You can assume that it's not sorted, right? So sorting might be even a step that you want to add.
Then in that case, you can kind of maybe do the complements again, but I guess from the first one, you start from the beginning. So let's say initially, yeah, like before, if you had like the you're looking for 9, and you have a 2 at the beginning of the array, you can subtract 2 from 9 and then search for the 7 in the array, and keep doing that for subsequent values. So the next one, I don't remember what the next value was. I think it was like 7, right? Or let's say we're looking for a different number, and just keep doing that and going through the array and searching for it.
Yep.
Well, after sorting it, of course.
Yeah, Wilma, thanks for suggesting it. Yeah, I think you have the right direction. So just to kind of like go over the answer. So yeah, I mean, you could use binary search here, and in order to kind of like make sure you can use binary search, you have one requirement, which is that the input array has to be sorted. So in order to kind of make sure if the input is, hasn't been sorted, you might want to do like apply a sort function or sort method to it. So then now your input is definitely for sure sorted. And once you have like a sorted array, then you can start like running a binary search against it. And as Wilmer said, the kind of basic idea here is that you want to basically like look at the value that's pointed by the middle index, and then oh sorry, you basically want to, what you want to do is you want to see if the complement of the current value is basically in this array. So what you do is like you basically subtract the target minus the current value, so to get the complement value, and then you try to like use the binary search to look up if that complement value is in this array or not. And depending on what the binary search tells you, like that that value may be like too high or too low. So depending on whichever way, like you want to cut down the search space in that direction. So this is kind of like the implemented solution. The sibling index that's returned by this binary search, this is like all pseudocode. It's basically telling you, where that value, what that value is located within this like array. And then once you have that, then you can kind of see, basically if it returns like it's like some value, then you have you basically have a valid answer, and if it doesn't, you can return false. One additional check that you may want to do is that you want to check if the value that's returned by binary search is like not the current value itself, because otherwise you would be basically like, even though there's like only one number, you're using that same value again, right? So you could imagine, if the target number is 10 and the current value is 5, you don't want to use that current value 5 again. You want it to like make up to that number 10. So you want to make sure there's like another 5 there to kind of get you there. So to kind of like do checks against those cases, you basically have to do these kind of condition check where you might want to compare against that number that's like that's before you or before the current value. That's like, before the value that's pointed by the sibling index, or the value that's pointed by by it after. But you basically want to check both before and after. So yeah, moving on to the runtime analysis. As you can imagine, the standard sort takes O of n log n, and then we're basically doing an n operation of binary search, in which each binary search takes O of log n time. So the total runtime of the binary search is also O of n log n. So in total, you have O of n log n for both sort and binary search, and because they're equal, the runtime still comes down to O of n log n. So this is how you might, you could use binary search in the case of two-sum problems when there's like some kind of requirement around not introducing additional space. So hopefully this was an interesting variation of this problem to go over. And now to kind of go over the second example, this problem is called sparse search. And basically the problem goes like this, which is that you're basically given a sorted array of strings, but this sorted array is interspersed with empty strings. So that's the input that you have. And you want to write a function or method that can find the location of a given string or target string, essentially. So the questions to be asked here is like, okay, first of all, what do we know about the input array? Well, just from like reading from the problem statement, we know that they're both sorted and interspersed with empty strings, meaning they're kind of like located in various places. So those are the two things that we know about our input. But what about those properties, especially the latter property that makes it hard to do a vanilla binary search?
Oh, you can't compare against empty strings or null.
Right, which is going to be impossible to do, right? For example, the value that's pointed by your binary search, if it's returning empty string, then you're like, whoa, okay, well, I don't know what this is telling me. And I also can't compare it against this target string that I'm trying to search for. And I don't know which way I need to go. So that's the kind of problem that you run into.
Yeah, maybe a nice analogy is you're hunting for that name in the phone book, but the phone book has ads in random places. So you might open to your midpoint and it's just ads and you don't actually see what point you're at in the address book.
Wow, that's a great analogy. Yeah, so you could imagine, yeah, when you open up a page, as Max said, the bunch of ads, and you're still looking for this person named Max Smith and Max McCord, and you just don't know which direction you want to go, right? So what do? Well, if you're a person and can only look at one page, you might just try to arbitrarily pick one direction to go to. And this way the next page has like non-ad page or an actual valid page, in which you can like determine whether the direction that you chose is correct. Because if it still shows like Max, then you're good to go. But if it shows that, okay, if it starts showing a person named like maybe like Noah, then you already know that, okay, M is already passed and you want to go back to the other direction. So yep, as Wilmer and Max has kind of pointed out, but binary search is not going to work without handling these empty strings. So now the question of the strategy is, what do we do to handle these empty strings in binary search, right? As I kind of mentioned, you could imagine how you might do it with a real life like phone book, but with code. Any thoughts on how you can handle these empty strings and still kind of carry on with your binary search?
Well, if it's empty, we can just say move on, right?
Well, how do you move on? You can definitely detect the current value is an empty string, but what do you from there, and how do you move on?
I guess we can just compare the left value and the right value and see which one is bigger.
Yep, I kind of like that direction. Is there a way to do both at the same time?
Yeah, we can just compare both at the same time, the left and the right, and then if the right is bigger, then go to the right. Well,
Right.
I mean, it's bigger than what we're looking for, right?
Right.
Yeah.
Exactly. So ideally, we can like do this search in both direction, in both like left and right of this value that's being pointed by the middle index or binary search, because you just don't know where is like the nearest like non-empty string is located, right? On the left side, it might be like, X number of like strings away. On the right hand side, it might be like Y number of strings away. And you just don't know whether X or Y or going left or right is going to get you to the closest one. So yeah, you could do both. So you can basically add a handler to find the nearest non-empty string in both directions. And just to kind of show you guys how this code works, this is more like a recursive part of this like search function. And and this kind of interface or parameters might be similar in that, yeah, you basically have like this like strings that basically suggests your input string. The second string or str is basically the current string. And then the first and last is like your like basically left and like right indexes that you want to kind of like bound your search space by. So as with usual, like you have like some like condition checks to make sure that it's not going into like invalid conditions. You also want to always kind of calculate your mid index, which you can easily get by adding the last and the first, or you can also think about it as like a right and the left index and divide it by 2 to get to the mid index. So once you have that mid index, you want to like see if the string that's pointed at mid index is empty, right? And if so, this is like what you kind of do handling. So here, what you want to do is like, okay, well, now I know that the value that's being pointed by mid is like empty string. So I need to basically make my both of these indexes left and right into like the one index that's like, both to the next of each other. So left would be mid -1 and right would be mid +1. So then they kind of move one space away from each other. And then you have this while loop in which you're just like literally just trying to search for like the next non-empty string. So one example here is that here, like for right, like if you check that if right is also less than or equal to last, and then finally when they finally equal to non-empty, then that's when you find that's when you got you found yourself a new mid. And similarly, you can also do it against the other side. And also try to find a mid. Otherwise, as soon as you find that, you can kind of break out of this while loop. But otherwise, what you do is you keep implementing, right? So you keep moving that pointer for the right and the left index by 1 over. So then they keep moving away from this like first like empty string that you found and try to find the next non-empty string. And this is the rest of the code, but you can imagine, yep, once the string, basically once the string that's like pointed by the mid index equals to this target string, then you finally found that index. Otherwise, you can like call this recursive function and try to keep kind of like tightening the search space by entering these like new indexes. That's basically essentially cut in half. And then this main function is basically some like wrapper function that, that's basically being wrapped around this recursive function. So so that's kind of like an interesting way to handle this special case in which your input is interspersed with like these empty strings. Yep. And do you guys have any questions on that? Okay, if not, then I'm going to just move on to my last example today, which is the cut width problem. This is actually one of my favorite coding questions, and it's really, really interesting. So I'm actually not going to get into the solutions for today. I probably would like you guys to like take this as like a take-home exercise and see if you can solve it. And just a heads up, like just by reading this problem, like right off the bat, you might not get that this is the way you could use binary search to get to the answer. But the problem kind of goes like this. So you're given n pieces of wood with lengths of like L of I. So basically you got n pieces of wood and this length is basically specified in this like integer array. And then you basically, once you have those n pieces of wood, you want to cut them into smaller pieces to guarantee you have k or more pieces of same length. So, and then the question asks, like, what is the longest length you can get from n pieces of wood? Okay, so when you first look at this question, you're like, whoa, wait a minute, why there's so many like variables like being thrown at me, right? And you might get confused. I mean, I'll probably feel that way when I first read this question. But just to unpack it a little bit, basically just like what problem is saying is, so imagine like in this example, you're given 3 pieces of wood, and this is the length that's being given with L. So first piece of wood has a length of 5. The second piece has a length of 9, but just for sorting purposes, being placed here. And then last piece of wood has a length of 7, right? And this K number basically means that, hey, we want to basically have at least 3 or more of like equal length pieces of wood. And then basically we want to make sure that we can kind of chop them and so that and they have the same length, and we also have at least this many number of them, right? So in this case, like right off the bat, you might see that, okay, well, why don't we try cutting by 5, because that's literally like the max number that you can cut any of these woods into. Doesn't really make sense to cut the wood by 7, for example, because I mean you can cut the wood with length of 7 and 9, but you can't really cut it with like wood of length 5, right? Because that's going to be kind of physically impossible. So you might start out by saying, okay, I'm going to just try cutting with the max possible length of 5 and see how many pieces that gets me. And in this case, I mean, it actually gets you 3 equal pieces of length 5. So that's kind of like one example. The second example is, once again, you have the same number of wood with the same length, but now instead of like wanting a 3 equal lengths, we would like to have 4 equal lengths of it, right? So now we can no longer cut it by 5, because if we cut it by 5, to kind of go back to the same example, to the last example, we can only get 3 equal pieces, right? But now we want at least 4 or more equal pieces. So then what do you do? Okay, so you know that, okay, length of, if you cut it by length of 5, it's not going to work. So you're going to try to like shorten your cut. So now you're going to try to get like a length, you're going to try to cut into pieces of length 4 and see if that's going to like do the job. And in this case, well, it actually does, because I mean, you can only get 1 piece of length 4 from this first piece of length 5. Same thing here with length of 7. But with this wood piece of length of 9, you can actually get 2 pieces of length of 4 out of it, right? We can basically divide into just like 2 pieces of 4, and it still like kind of give you this remainder of 1, which is kind of wasted for this thing, but that still gives you 4 equal lengths pieces. So you can kind of imagine this is like in a brute force solution, this is actually what you might do, which is basically like you might want to just try with like a max possible length and see if that kind of gets you the K equal pieces of wood that you need, and just incrementally go down, like basically try smaller pieces and like one at a time, right? But you can imagine that's going to lead to like a greater runtime, because you have to try every possible length, right? So yeah, so the question becomes, okay, well, how can you optimize it? And as we kind of like imagine with today's topic, the answer is to do a binary search. And to kind of quickly go over this in the interest of time. So if you basically, what you want to do is you basically want to use binary search to find the possible max length, right? So that's kind of like the top level idea that we have. So then from there, what we want to do is, well, for each candidate length, we also need to calculate how many wood pieces of that length can be cut out, right? So so like let's say we have some number from like 1 to 10, because 10 is probably the longest, like the max possible like length in which we can cut these woods into, right? So you might want to start with like length of 5 and see how that does, right? And these are the conditions that you want to basically have, which is if that kind of like possible candidate satisfy the target number of pieces K, then the max length can possibly be longer than the candidate length. So now you want to do a binary search against the longer half of the remaining possible lengths. So now you might want to even like try any of the numbers from like with length 5 to 10, but in the principle of just following the binary search and making it more efficient, you want to try like length of 7 or length of 8. On the other hand, if that number does not satisfy the target number of pieces k, then the max length has to be shorter than the candidate length that you just tried now. So what you want to do is you want to do binary search against the shorter half of the remaining possible lengths. So you want to look at the pieces from like length of 1 to 5 in that case. And in the principle of like binary search, now perhaps the next steps you want to try is try with like this cut length of 3 and see if that's going to work. And basically you want to repeat this process until you're left with like one possible length, which also has to be like the max length for this case. So that's the high level strategy that I'm going to share with you guys. In terms of implementation, we'll leave it off to you guys for your take home exercise. But that wraps up the lesson for today.
I have a question. Is there does one of the weeks cover min heaps and max heaps?
Good question. We actually don't cover that. But yeah.
I think it's a good one to know. Almost like on the level of like, it's kind of a joke with interviewing. If you can't figure out how to make something faster, just throw a hash map at it. I think a min heap or a max heap, that's another one of those data structures that's is super useful in a lot of use cases. And it's kind of related to sorting and searching. And this data structure, a min heap, is where like you get constant time access to the lowest element at all times. And insertion into those is usually the implementation is a balanced binary tree. And then when you're inserting an element, you basically find the place in the tree to insert it and then swap it around so that it remains balanced. And the minimum element is always like at the top, or the maximum element. A use case of that you might think of is like a queuing system, where you have the system that's you're queuing jobs and you have to say, you're saying at 4 p.m. do this task, at 4:01 p.m. do this task, at 6 p.m. do this task. You know that when you're looking at what task you should do, you want to look for the like most immediate task that's about to happen of all the ones scheduled. So if you're storing your tasks in this min heap, you know that top element, you get constant access to the like next event that needs to happen. And then every time a new one comes in, you insert it into your heap and it stays sorted and you always have access. So that's a good one to know. That's like a super quick thing. I feel like you could do a whole lesson on that, but definitely want to do more research on your own time.
Yeah, that's a good call out. We do have, I think our next one after this is graphs and trees, unless we already, yeah, I think like next one after this is graphs and trees. And so we could make it like we could either append it onto that lesson or we could add like a little supplementary video after.
Yep. Yeah, great. I think that's a great suggestion in order to kind of couple with this lesson. Right. Let's see. So yeah, now we want to kind of open up the floor for any Q&A. So if you guys have any questions about today's lesson or any question that you want to ask Max about in terms of career navigation, feel free to post them into the chat or just voice them out loud.
Max, did you say what team you're on at Google?
Yeah, I went over a few different teams that I was on. Yeah, I saw your DM, Horacio. Yeah, sorry I haven't gotten back to you. I've been a little busy, but I promise to take a look at that. Yeah, so I can kind of go over it again. The team that I'm on currently, so the hardware org that I'm in is, the product area that I'm in is hardware, so Google Nest. So that's all of the physical products that you see, like Chromecast, all of the smart speakers, the smart displays, and then more recently things like Stadia, the gaming, cloud gaming stuff. That's all under our umbrella. And I've done a few things. I've done server development for the front-end server that serves the Google Home app. So that's the app you're using to like configure your devices and set up your home and stuff. And then I've done development like sort of deeper in the microservices architecture in the business layer, actually implementing some of the functionality of that subscription service. And then currently I'm on the growth team, sort of enabling promoters to run these promotions to like give out coupons, discounts, or free devices, things like that.
Yep, yeah, that sounds like that's like a lot of interesting work. And I'm also kind of curious, but was it hard for you to kind of transition from like low level programming that you were doing at your previous company to doing like web development, like such a large scale in places like Google?
Yeah, it's very different. And I think it's more about finding the right fit for you, more than saying like something is bad to work on or good to work on. Because I actually was really interested in the low level stuff that I was doing. And I learned a lot working at National Instruments, especially about how operating systems work, understanding how there's microcontrollers on the back plane of a PXI chassis that we had. And that microcontroller, if any of you have taken like an assemblies class or something, it needs to be able to communicate to the actual operating system of the computer somehow. And so you learn about how like the microcontroller is writing to some register and then on its thing, and then that gets mapped to like memory lines on the PCI bus, and then the processor like assigns some memory address space to that register so that you can read from the register of this device as if it were RAM or something. That's really interesting to me to understand how all that low level stuff worked. The life cycle of that was like a lot more slow than something that's web based. And we basically had a release like twice a year. So we would write code, like implement new features and stuff, and then there'd be a big release twice a year, and that would be like the driver DVD. And so leading up to the release, there'd be a month or two of just testing where we're trying to guess like all these different situations and system combinations that our customers would run into to make sure there's no bugs. Then we release it. If there's any bugs that get reported back to us, we have to do a patch, release that as a patch. I think as I was leaving, they were starting to get to a more iterative process where they would release more often. That's the kind of thing you see where maybe you're in your day-to-day using a computer. It's like you sign up for like automated updates, automated driver updates that just run on when you start up your computer. I think that's a little more ideal. Releasing more often and getting feedback a lot more often is better. But that's what we had then. So switching to this like web-based company was a huge difference to me because when we write code, instead of like, oh, there's going to be a release in 6 months and we'll test it in this big testing phase, it's like when you write something, it goes out live usually the next week or 2 weeks, and you get that immediate feedback. And the systems are a lot more alive. So like you're deploying your code and you're usually like instrumenting it with some kind of like, every time someone sends in a request that looks like this, add one to a counter. And then when it gets released, it'll be like 1% of all the servers in your huge fleet are running your new code. Traffic starts coming in and you see your counters start to rise, and you get to see a graph in real time of people running your code and like the different conditions. You roll it out to 10% of the fleet and eventually 100% of the fleet, and you get to see that traffic coming in real time. If there's any problems, you do a rollback, see that graph drop to 0. So that is like super interesting to me, stuff like running 24/7. You start to get into things like having to have an on-call because if anything goes wrong in the middle of the night, someone has to wake up and figure out that issue and get it working again because if Google.com stops responding, there's like a real monetary loss to the company. Whereas problems when I was working on driver development was more like customer got their machine into a weird state and we have to like fix that for them. But do it during business hours or something. There's a big difference in terms of like the feedback cycle being a lot shorter, feeling like things are alive. I think that's pretty exciting, which is why I like it a lot more.
Yep. Yeah, that's a really cool story. I feel like it's really interesting to hear from someone who has kind of gone through both sides of like software engineering, like both web and like non-web, especially with like embedded systems and low-level programming. So yeah, thanks for sharing that. But yeah, do we have any other questions that that anyone wants to ask for Max? Okay, well, if we have no questions, I would like to respect your time since we're a little bit running over. So thank you so much for joining us today, Max. And for the fellows, yeah, I will follow up with today's like slides and recorded lessons and all that on the Slack channel. So please be on the lookout for that. otherwise, thank you guys so much and have a nice day.
Have a good one all.